Tonight, we're going to talk about something that sounds simple, but is actually one of the most confusing ideas in all of science. Spacetime. You've probably heard this word before. Scientists throw it around constantly. Einstein's theory of spacetime. The fabric of spacetime. Spacetime is curved, but here's what most people don't realize. When you actually dig into what spacetime means, when you try to understand what it really is, you discover something unsettling. We don't know. We use this idea every single day. Your GPS wouldn't work without it. We've photographed it being bent around black holes. We've detected ripples moving through it. And yet, we have no idea what it actually is. By the end of tonight, you're going to understand why this is one of the biggest unsolved mysteries in physics, and why solving it might change everything we know about the universe. Before we dive in, if you're interested in this kind of deep exploration, a quick like or subscribe really helps the channel grow. It makes a huge difference. Now, let's begin. Let's start in 1905. Albert Einstein was 26 years old, working as a patent clerk in Bern, Switzerland. He wasn't a professor. He didn't work at a university. He examined patent applications for electromagnetic devices during the day and thought about physics at night. And in that year, 1905, he published 4 papers that would change physics forever. One explained Brownian motion and proved atoms were real. One explained the photoelectric effect and helped establish quantum mechanics. And 2 papers introduced what we now call special relativity. Special relativity sounds complicated, but the core idea is actually straightforward. Einstein realized that the speed of light is always the same, no matter how fast you're moving. This seems impossible at first. If you're on a train moving at 100 kilometers per hour, or about 62 miles per hour, and you throw a ball forward at 20 kilometers per hour, or about 12 miles per hour, someone standing on the ground sees the ball moving at 120 kilometers per hour, or about 75 miles per hour. The speeds add up. That makes sense. That's what we expect. But Einstein showed that light doesn't work this way. If you're on a spaceship moving at half the speed of light, and you shine a flashlight forward, you might think the light would move at 1.5 times the speed of light from the perspective of someone watching you. But it doesn't. The light moves at exactly the speed of light, about 300,000 kilometers per second, or about 186,000 miles per second, both from your perspective and from the perspective of someone watching you from outside. The same speed. Always. This seems impossible. How can light be moving at the same speed for both observers when one observer is already moving at half the speed of light? Einstein's answer was radical. Space and time adjust to keep the speed of light constant. If you're moving very fast, time literally runs slower for you from the perspective of someone standing still. And distances in the direction you're moving actually contract. They shrink. These aren't optical illusions. They're real physical effects. Time and space are not absolute. They're relative, depending on your motion. The only thing that's absolute, that's the same for everyone, regardless of how they're moving, is the speed of light. This was shocking in 1905. It overturned centuries of assumptions about how the universe works. Newton had built physics on the idea that time flows the same for everyone, that a second is a second, no matter where you are or how fast you're moving. Einstein showed that wasn't true. Time is flexible. Space is flexible. They bend and stretch depending on your motion. Think about what this really means. If you could build a spaceship that travels at 99% of the speed of light, and you took a journey to a star 10 light years away and back, from your perspective on the ship, the journey might only take a couple of years. But when you return to Earth, 20 years would have passed. Your friends would be 20 years older. Your children might now be older than you. This isn't science fiction. This is what Einstein's equations predict. And it's been confirmed by experiments countless times. We've tested this with particles in accelerators. Unstable particles that normally decay in microseconds live much longer when they're traveling at 99.9% of light speed. We've tested it with atomic clocks on airplanes. When you fly an atomic clock around the world and compare it to an identical clock that stayed on the ground, the traveling clock shows less time has passed. The difference is tiny. Just a few hundred nanoseconds, but it's measurable, and it matches Einstein's predictions exactly. The implications are profound. There's no universal now. No cosmic clock ticking at the same rate everywhere. When you say something is happening right now on a distant planet, that statement has no absolute meaning. Different observers moving at different speeds would disagree about what right now means. They disagree about which events are simultaneous. Time is not a river flowing at a constant rate for everyone. It's more like a fabric that can stretch and compress depending on how you're moving through it. But Einstein wasn't done. Special relativity only dealt with objects moving at constant speeds. It didn't handle acceleration, it didn't handle gravity, and gravity was a problem. Newton's law of gravity had worked brilliantly for over 200 years. You could use it to predict the motion of planets, the trajectory of cannonballs, the orbits of moons. It was one of the most successful theories in the history of science. But Einstein realized it couldn't be right. Not completely. Newton's gravity worked instantly. If the sun suddenly disappeared, Earth would immediately fly off into space, according to Newton's equations. The gravitational pull would vanish instantly across 150 million kilometers, or about 93 million miles of empty space. But Einstein had just shown that nothing can travel faster than light. No signal, no force, no information can cross space instantly. If the sun disappeared, it would take about 8 minutes for the light to stop reaching Earth. That's how long light takes to travel from the sun to us. And Einstein realized gravity couldn't work any faster than light either. There had to be a delay. Something had to carry the gravitational force, and whatever it was couldn't move faster than light. This led Einstein to one of the most productive thoughts of his life. He called it the happiest thought he ever had. It came to him in 1907. He was sitting in his office at the patent office, thinking about gravity, when he imagined a worker falling off a roof. While the worker is falling, Einstein realized the worker doesn't feel their own weight. They're weightless. They're in free fall. If they dropped a hammer while falling, the hammer would float next to them, falling at the same rate. They wouldn't see the hammer accelerate away or toward them. It would just hover there in mid-air from their perspective. This seems obvious now. We've all seen footage of astronauts floating in the International Space Station. But Einstein realized something profound. The worker falling off the roof and the astronaut floating in space are experiencing the same thing. They're both in free fall. The astronaut isn't actually floating in zero gravity. They're falling toward Earth, just like the worker. But they're also moving sideways, fast enough that they keep missing Earth. They're in orbit, continuously falling, but continuously missing the ground. And that's why they feel weightless. Not because there's no gravity, but because they're in freefall. Einstein realized that being in freefall is indistinguishable from being in empty space with no gravity at all. And being in a rocket accelerating upward is indistinguishable from standing on the surface of a planet feeling gravity pull you down. You can't tell the difference. If you're in a closed room with no windows, There's no experiment you can do to determine whether you're sitting on Earth's surface feeling 1 g of gravity or sitting in a rocket in deep space accelerating upward at 1 g. The effects are identical. This is called the equivalence principle. Acceleration and gravity are equivalent. They're the same thing. And this was the key insight that led Einstein to his theory of general relativity. If acceleration and gravity are the same thing, and if special relativity says that acceleration affects space and time, then gravity must also affect space and time. Gravity must curve space and time. It took Einstein another 8 years to work out the mathematics. From 1907 to 1915, he struggled with the equations. He learned advanced mathematics he'd never studied before. He made mistakes, published wrong results, corrected them, and tried again. It was the hardest work of his life. He later said the final year, from late 1914 to November 1915, was the most exhausting and demanding time of his entire career. But in November 1915, he finally got the equations right. He published his theory of general relativity, and physics would never be the same. General relativity says that mass and energy curve spacetime, and objects moving through curved spacetime follow curved paths. That's what we experience as gravity. It's not a force pulling objects together. It's objects following the straightest possible paths through this warped geometry. Those paths just happen to curve because the geometry itself is curved. The classic analogy is a rubber sheet. Imagine stretching a flat rubber sheet taut. If you place a heavy ball in the middle, it creates a dip, a curve in the sheet. Now, if you roll a smaller ball across the sheet, it will curve toward the heavy ball. Not because the heavy ball is pulling it, but because the sheet itself is curved. The small ball is trying to roll in a straight line, but the curved sheet forces it to follow a curved path. This is what mass does to spacetime. The Sun, with its enormous mass, curves spacetime around it. Earth is trying to move in a straight line through space. But the curved spacetime around the Sun forces Earth to follow a curved path. That curved path is Earth's orbit. We experience this as the Sun's gravity pulling on Earth. But from Einstein's perspective, there's no pull at all. There's just Earth moving through curved spacetime. Now, this rubber sheet analogy is helpful, but it's also misleading in some ways. The rubber sheet is a two-dimensional surface curving in three-dimensional space. But spacetime is four-dimensional, 3 dimensions of space plus 1 of time, and it's not curving in some higher dimensional space. It's curving in on itself. This is hard to visualize because we can't picture 4-dimensional geometry. Our brains evolved to understand 3 spatial dimensions, not 4-dimensional spacetime. Also, the rubber sheet analogy makes it look like gravity is pulling the balls down. But that's our Earth gravity doing the pulling in the analogy. In real spacetime, there's no external force. The curvature itself is gravity. Objects follow geodesics, which are the straightest possible paths through curved spacetime. A planet orbiting a star is following a geodesic. It's moving in what it thinks is a straight line, but because spacetime is curved, that straight line curves back on itself, creating an orbit. Einstein struggled for years to find the right mathematical language to express these ideas. He needed tensor calculus, a branch of mathematics that deals with objects that have multiple indices and transform in specific ways when you change coordinate systems. He'd never studied this in detail during his university education. He had to learn it from his mathematician friend Marcel Grossman. Together, they worked through the mathematics, trying different formulations, making mistakes, publishing preliminary versions that turned out to be wrong. At one point, Einstein thought he had the right equations, published them, then realized they didn't reduce to Newton's law of gravity in the appropriate limit. That should have been a red flag. Any new theory of gravity has to match Newton's predictions when gravitational fields are weak and objects are moving slowly, because Newton's theory works perfectly well in those situations. Einstein's preliminary equations didn't do this. So he went back to the drawing board. The breakthrough came in November 1915. Einstein was in Berlin, working feverishly on the equations. He gave a series of lectures at the Prussian Academy of Sciences, presenting his progress week by week as he refined the theory. On November 25, 1915, he presented the final form of the field equations. These 10 interrelated equations describe how the curvature of spacetime is determined by the distribution of mass and energy. They're beautiful in their symmetry and elegance. They can be written compactly as G equals 8 pi t, where G is the Einstein tensor describing the curvature of spacetime, and T is the stress-energy tensor describing the distribution of mass, energy, momentum, and pressure. These equations are deceptively simple looking, but solving them for realistic situations is extraordinarily difficult. They're nonlinear partial differential equations. The curvature affects how mass and energy behave, but mass and energy also affect the curvature, creating a feedback loop that makes the equations very hard to solve. For most realistic scenarios, you can't solve them exactly. You need numerical simulations run on powerful computers. Even today, with all our computational power, solving Einstein's equations for complex situations like two black holes colliding requires massive supercomputers running for weeks or months. This was a beautiful idea. It was elegant. It explained everything Newton's gravity explained, but in a more fundamental way. And it made new predictions that Newton's theory couldn't account for. One of the first successes was explaining the orbit of Mercury. Mercury, the closest planet to the Sun, has an orbit that's slightly off from what Newton's equations predict. The point where Mercury is closest to the Sun shifts very slightly with each orbit. This is called the precession of Mercury's perihelion. Astronomers had known about this for decades and couldn't explain it. Some thought there might be another planet closer to the Sun than Mercury, pulling on it and causing the shift. But Einstein's equations predicted the exact amount of precession without needing any extra planets. Spacetime was curved more strongly near the Sun, and that extra curvature explained Mercury's strange orbit perfectly. But the real test came in 1919. Einstein's theory predicted that light would be bent by gravity. More specifically, starlight passing near the Sun would be bent by the Sun